So first, what we're going to do is talk about what's called the autoionization of water. And this is going to lead us to the idea of pH, which most people think of when they think of acids and bases. So the autoionization of water is when we have two molecules of water and one acts like an acid and one's like a base. We'll look at it on the next slide. So the equilibrium value for the autoionization of water looks like this, and we're actually going to derive it on the next slide. So Kw equals H3, the concentration of H3O plus in molar concentration times the molar concentration of OH negative. The value for Kw is 1.0 times 10 to the minus 14th. That's at 25 degrees Celsius, which is pretty much what we'll be using. Yeah, so it can change with temperature. We'll pretty much just be using the Kw value, assuming that we're at 25 degrees Celsius. All right, so the autoionization of water is really important. And autoionization, just what the word means, it ionizes itself. So in the case of water, here's our reaction. Two H2Os react, one acts like an acid, one acts like a base. So obviously we can't tell from this reaction which one acts like an acid, which one like a base, but let's say this one gains that H plus, so it's acting like a base, and this one's donating an H plus, so it's acting like a base, like an acid, so here's the conjugate base. And here's the conjugate acid. Of course, it could be the other way because we don't know which H gave up, but this is your equilibrium. Remember how we can write an equilibrium expression? That K expression is just the products over the reactants. Well, because this is only a very minor part of water. Some of the water will ionize, but most of it will just stay as plain old H2O. So in most senses, H2O concentration will be pretty much constant because it doesn't change very much with the autoionization. So if we assume that's a constant, we can multiply both sides by the H2O plus squared. So we have a constant times a constant, which of course is just a constant, and we're going to call that constant Kw. So that's where this equation is derived from. So it could be H3O plus, so Kw, we saw it earlier, H3O plus. Remember, again, H3O plus and H plus are really interchangeable. So a lot of people will write the H plus just because it's easier, but it means the same thing. So Kw, remember Kw 1.0 times 10 to the minus 14th. So if you're in a neutral water, because that last reaction that we looked at is 1-to-1, that means that the H plus and the OH negative concentrations have to be equal to each other. So since they're equal to each other, if you take the square root, so yeah, if we just say H plus is equal to X, so that means OH negative is also equal to X because they're equal to each other. If you take the square root, you get 1 times 10 to the minus 7th, which is the concentration of both H3O plus and OH negative in pure water. So they're both 1 times 10 to the minus 7th molar. So again, that's in pure water because everything's 1-to-1. But the nice thing about this equation is that it holds true for all aqueous solutions. So if you have acids, if you have other things in water, it doesn't have to be pure water, but if it's neutral, they're still, the H plus and the OH negative are still going to be equal to 1 times 10 to the minus 7th, even if there's other ions in there. As long as it's a neutral solution, this will be true. And or if you put some acid or base into water, they're no longer equal, but like I said, the expression still holds. So you can alter the concentrations of H plus and OH negative by increasing or dissolving substances that are acidic or basic. And so because they're equal to each other, equal to a constant, because the product is equal to a constant, that means that they are inversely related to each other. So if the H plus goes up, then the OH negative has to come down because the product equals a constant, and vice versa. So again, in a neutral solution, H3O plus equals OH negative. If you have an acidic solution, H3O plus is greater than OH negative because it goes up and OH negative comes down. And then in a basic solution, OH negative is greater than H3O plus. So same thing. So looking at it from a different perspective, in an acidic solution, H3O plus has to be greater than 1 times 10 to the minus 7th, and OH negative is then less than 1 times 10 to the minus 7th molar. In a neutral solution, they're equal to each other, equal to 1 times 10 to the minus 7th, and in basic solution, they are the OH negative is less than 1 times 10 to the minus 7th. OH negative is greater than 1 times 10 to the minus 7th. So it's kind of that 1 times 10 to the minus 7th is kind of that tipping point. And that 7 comes up and you're like, oh, pH 7 is neutral. So definitely pH is related to this exponent here. So let's take a look at that. All right, so if you have a solution of a strong acid, you can normally ignore the self-ionization of water. So you just have a lot of H plus in there. And I really want you to keep this in mind throughout the rest of this chapter. Remember that in chapter 4, we talked about 6 strong acids to remember. And the thing that we talked about in chapter 6 was that these 6 strong acids completely dissociate. HCl, HBr, HI, HClO4, HNO3, and H2SO4. And I will say that the H2SO4 will only lose the first H. Only the first H is considered a strong acid. But you want to remember these 6 when we get into weak acids and bases. But the important thing is that, so like I said, they completely react with water or they completely dissociate. All of the H plus will go into water. And so the H3O positive concentration there is determined by whatever the concentration of the acid is. So in other words, if it's a strong acid, you can ignore the H3O plus that comes from the auto-ionization of water and just use the concentration of the acid because that's dominant. But because the self-ionization still exists, we can figure out what the OH negative ion concentration is by using that equation. So, for example, calculate the concentration of OH negative ion in a solution that's 0.1 molar HCl. All right, because HCl is one of the strong acids, we can assume that if it's 0.1 molar HCl, because it completely dissociates, sorry, didn't mean to cross that out, because it completely dissociates, that means that the H plus concentration is equal to 0.1 molar. So because H plus is 0.1, and because this equation is true, we can solve for OH negative. So OH negative equals 1 times 10 to the minus 10th divided by 0.1, or 1 times 10 to the minus 13 molar. Clearly, this is an acidic solution since the H plus is greater than 1 times 10 to the minus 7th. And you can see here that OH negative is clearly much less than 1 times 10 to the minus 7th. So this is an acidic solution, but we can actually now calculate what the values are. And clearly H plus is much bigger than OH negative, but that OH negative is still present to a very, very small extent. In the same way, if we have a strong base, we can ignore the self-ionization of water as a source of OH negative. So again, really important to remember this. Like if you're taking a test and you want to write something on your card, you definitely want to know what are the 6 strong acids and 6 strong bases. These are the 6 strong bases that we talked about in chapter 4. LiOH, NaOH, KOH, CaOH2, SrOH2, and barium hydroxide, BaOH2. So these, again, they're considered strong bases because they completely ionize. And what I want you to be careful is if you're using one of these last 3, remember that if they completely dissociate, then the OH concentration actually in this case will be twice the concentration of the base. So I think I have an example of that coming up. So these completely dissociate. That means the OH negative concentration is determined by the strong base concentration. However, there is still some H3O plus around, and we can calculate it using that expression. So calculate the H plus concentration if we have a 0.010 molar NaOH. So because we started with NaOH considered a strong base, we know that it completely dissociates. 0.010 molar. And if we substitute the OH negative 0.010 into this expression, we can solve for H plus. And so 1 times 10 to the minus 14th divided by 0.010 is 1 times 10 to the minus 12 molar is the H plus concentration. Again, the H plus is much less than 10 to the minus 7th. The OH is much greater than 10 to the minus 7th. And it's clearly basic. I don't think I did an example like this, but what if it was 0.010 molar calcium, like I said, calcium hydroxide, then just be careful here, the OH negative concentration will be double that, so it will be 0.020 molar. So in that case, you would plug in 0.020, and you'd have it's going to be even a little bit more basic. So 1 times 10 to the minus 14th divided by 0.020 will be 5 times 10 to the minus 11th. And so 5 times 10 to the minus 13th. So actually it'll be even a little less acidic, more basic. So I just wanted you to be aware of that. If you have one of those barium, calcium, or strontium, make sure the OH concentration doubles for whatever this is, because the OH completely dissociates. All right, so here we are finally with pH. I mentioned it earlier, but let's talk about it now. So we can describe the acidity of a solution by its H3O plus, but we're dealing with those really small numbers, and so that's where pH came in, because it's actually taking those small numbers and making them into something more usable, more convenient. So this is the definition of pH. pH is the negative log of the H3O concentration. So depending on the calculator you have, if you have like a fancier graphing calculator, you'll put it in just like this, negative log, whatever the number is. Sometimes if you have some of the cheaper calculators, you have to kind of do it going outward. You have to put the concentration in and then hit the log button and then hit the negative button. And if you're having trouble with a calculator, let me know. I can either show you in lab or set up a Zoom or something so that you can see what's happening. Anyway, this is going to be a calculation you'll definitely have to be able to do. All right, so if we have a H plus concentration, so we're doing the simple things, and now you can see logarithm. So a logarithm just is connected to that exponent. So if a number in scientific notation is 1 times 10 to the minus 3, then the pH is just 3. Couple of things to keep in mind. Significant figures. because the concentration has two significant figures, technically this 3 is not significant. It's like a placeholder because it's related to the exponent. So the number of sig figs that we want is just the decimal. So if you have 2 sig figs in your number, you want 2 decimal places in your pH. If you have 3 sig figs, you'll want 3 decimal places in your pH. So just keep that in mind in terms of sig figs. We'll get a number between 2 and 3 if this number, if this number is not, like if it was 5 times 10 to the minus 3, then my my pH would not be a whole number. Again, so now we can see that a neutral solution, H plus, is 1 times 10 to the minus 7th. So the negative log of 1 times 10 to the minus 7th is 7. So that's where your neutral pH comes from. And so now we can add to our list for acidic solutions, pH has to be, since H plus is greater than 1 times 10 to the minus 7, and remember, because what is that, 1, 2, 3, 4, 5, 6, 7, because a number greater than this would actually have a smaller negative exponent, so that's why the pH is less than 7, because obviously if you have 1, 2, 3, 4, 5, 6, yeah, so I have 1 fewer O, so this is 1 times 10 to the minus 6, so that's definitely a bigger number, bigger than that, and this would be a pH of 6, because it's 1 times 10 to the minus 6. So that's why the concentration, as that exponent gets smaller negative, the pH gets smaller. So that's why the lower the pH, the more acidic it is. So similarly, a basic solution will have a pH greater than 7, because remember the H plus, we're talking about the H plus concentration. So if it's a basic solution, the H plus concentration will be greater than 1 times 10 to the minus, or it'll be less than 1 times 10 to the minus 7th, which means the negative x, it's a bigger number, a bigger negative exponent. So it's greater than 7. So let's look at the next chart. These are just some, so here's neutral, 10 to the minus 7th. You can see here's pH, 10 to the minus 7th. So here's all our pHs. This is the H plus concentration, and then the pH scale. So if it's greater than 7, it's basic. This just gives you some example. Blood is slightly basic. Seawater is slightly basic. Baking soda, ammonia is very basic. Milk of magnesia, which is antacid, so that's kind of makes sense that it should be very basic. Here's some of our carbonated water, sodas, things like that are acidic. Milk is slightly acidic. Vinegar, we know, is mostly acetic acid, and so it's very acidic. Stomach acid is hydrochloric acid, so it's very acidic. Anyway, you can see here the trend. So and just by the way, FYI, you can actually have a pH that's negative. So if you have a concentration greater than 1, if you have a HCl concentration that's greater than 1, you're going to have a negative pH. And you can have a pH greater than 14 too if you need to. So this is just kind of our normal scale, but it can extend. So again, just a summary. If H3O plus is greater than OH negative, is acidic. That means pH is less than 7. If they're equal to each other, pH equals 7. And if they're basic, OH negative is greater and pH is greater than 7. All right, so let's look at an example. A sample of orange juice has a hydrogen ion concentration of 2.9 times 10 to the minus 4th. What is the pH? Let's think about it. Well, it's orange juice. Orange juice has acetic acid, or vitamin C, ascorbic acid. So you probably already knew orange juice is acidic. And if you look at the concentration, this concentration is definitely greater than 1 times 10 to the minus 7th, so it's definitely acidic. But the question is, what is the pH? So we know our definition, pH equals negative log H plus concentration, so you're just taking the negative log of 2.9 times 10 to the minus 4. Just so you know, keep in mind that your pH, you're doing something wrong if your pH isn't close to 4. It's probably going to be slightly less than 4. So yeah, 3.54. So the exponent if it was 1 times 10 to the minus 4th, it would be exactly 4. If this number is a little bit bigger than 1, then it's going to be slightly less than 4. But it should be, really close, within within one digit, so 3.54. So that's a way to check yourself if you're doing something wrong. What about going the other way? What if you know the pH and you want to find out the concentration? So for example, the pH of human blood is 7.4, so slightly basic. What is the H plus concentration? So we want to do the inverse. So if pH is negative log of H plus concentration, then H plus concentration, the first thing we do is take the negative, and then we do the inverse log. So if we did the inverse log, we get H plus equals inverse log of negative pH, which the inverse log is just 10 raised to the negative pH. So 10 raised to the negative pH is 10 raised to the negative 7.4. Technically, that's an accurate number, but we like to put things in scientific notation, so that's 4.0 times 10 to the minus 8th molar. And we see that since its blood is slightly basic, we do expect our H plus to be slightly less than 1 times 10 to the minus 7th. Notice 2 decimal places, so 2 sig figs in my answer. All right, we can also measure something called the POH. So the P function is just a function that says take the negative log of whatever you're talking about. So in fact, POH is defined as the negative log of the OH negative concentration. Sometimes it's helpful to know that. Most of the time we only want to know the OH. Do keep in mind that you start to mess with your mind. It's going to be the opposite of pH. So here's why. So because Kw equals this, like if you took, so Kw equals H plus times OH negative. If we take the negative log of both sides, so negative log of H plus OH negative, the negative log of 1 times 10 to the minus 14th is 14. And actually, if you remember your rule of logs, if you take the negative log of a product, you can take the negative log, the sum of the negative log. You can take them out individually. You may or may not remember that from math classes, but the log of a the log of a product is the sum of the logs. So we have the negative log of the H plus the negative log of OH negative, so that's pH plus POH equals 14. So they're going to be opposite each other. So if pH is 7, POH is 7, of course, because 7 plus 7 is 14. If pH is 3, POH is 11. So the POH is a measure of the OH concentrations, and since they're inverse, they should be opposite each other. So there's a couple of different ways that you can do this problem. An ammonia solution has a hydroxide ion concentration of 1.9 times 10 to the minus 3 molar. What is the pH of this solution? So there's actually 2 ways you can do it. Probably the easiest way is to find the POH. Since we know the OH concentration, the POH is negative log 1.9 times 10 to the minus 3, 2.72. Now pH then is 14 minus 2.72, or 11.28. The other way you could do it, if you wanted to, there's no wrong way, they're just different. Remember Kw equals H plus times OH negative. So if you wanted to, you could take the OH negative, solve for H plus first using this equation, and then find the pH by taking negative log of H plus concentration. And either way gets you to the right place. So you could, if you like, I think people just like to go straight to the POH and then subtract from 14. But like I said, you could calculate it this way. So if you plugged in 1.9 times 10 to the minus 3, then H plus would be equal to 5.26 times 10. Now I'm mixing up my sig figures. 5.3, I guess. 5.3 times 10 to the minus 12. Let me make sure. 1, 2, 3. And then if you take the log of that number, you get 11.28. So negative log of 5.3 times 10 to the minus 12 is 11.28. So you could do it in either way. Both are fine. We can use what's called a pH meter to measure the pH. And so here's some, on the next slide, you can see some pH meters. We'll be using one in lab this semester. You can also use indicators to determine if the pH, we actually have some, we'll be doing that too. We have some wide range pH paper, which changes different colors depending on the pH. So here you can see pH meters. It measures the, because there are ions involved, it measures the amount of the ion, and so it's complicated, but it can be based to set to find the pH. And then, yep, so here you can have indicators. This is called a universal indicator. So if you put a couple of drops in very acidic water, it's red, and very basic solution, it's navy blue, and it could be lots of different colors in between. So, you know, this might be a pH of about, so this is a pH of about 1, this might be 3 or 4, and pH 7. And so then more basic gets more blue, more acidic gets more red. This is the paper I was talking about. You can have this wide range paper, so it'll change a different color, and you can match it to the chart to determine what the pH is.